Hello everyone, welcome to my YouTube channel, Precision Manufacturing System. Today I'm back with another interesting video regarding the DEM particle generator. But this time I would like to talk about another software, an open source software, which is called LIGGGHTS, which is widely used these days for DEM process and DEM simulation. Before getting started, I really ask you to subscribe our channel. Our channel really needs your support and motivation. Please support our channel and hit the like button and introduce our channel to your colleague and friend to be our strong motivation to continue and creating such a helpful video for you guys. Okay, let's start and let's start from here. Actually, for lights simulation, we need some geometry. Actually, if you want to have this kind of result or simulation, in this simulation, I would like to talk about and explain for monosphere and a single size of particle. Next time maybe I will explain for 2 or 3 and multi sphere size or distribution for generating. And for this kind of simulation we need something like this, a shell box, as you can see, which is called boundary or box. The real one should be 1 by 1 by 1, but in lights we need some extra space for creating the particle. And an inlet we have, as you can see in this figure, we put the inlet in the height of the 1 millimeter, and it's up to you, and you can change the dimension and also the diameter, the dimension of the inlet can change, and it's up to you. But for my case, and as you can see in this figure, the particle pours when it reach at the height of the 0.1 centimeter, and the x and y dimension is 1 by 1. Okay, this is a briefly explanation about our model, and let's continue with the simulation. And first we need to define our and prepare our let's say input file. But before, when you prepare your model or your geometry, you should save it as STL file, and before and after that, because when you want to load it or recall it in lights simulation, light simulation can read only STL format, and you need another software for running the lights input file. I used Ubion 2 for actually the running, or somehow they call it subsystem for Windows, because I'm using the Windows, but this software based on Linux software or Linux Windows because of that I'm using this software for running my simulation. Okay, these are a requirement for running the LIGGGHTS software, and when you are installing the software, you should actually install these subsystem to install the LIGGGHTS. Okay, now let's start. Here we have the atom style, and you should specify your atom style. Atom style is granule, and here we should specify the boundary type of the boundary of our simulation. I put FFF as a fixed for every direction, and you can put it M or P as a periodic boundary, and here we specify the units, and I used centimeter for my units, but you can change it or to your for your case. And also here these are constant and can be say for velocity of actually for particle. And here we should define our region for actually for box or boundary. As you can see based on the slide I showed you, we have from 0 until 0.1 for x and y, and this is 0.15 for z direction. And also we put 0.50 because of that, as I already said, we need some space, more space, extra space for creating the particle. Because of that I put 0.50, and actually it is up to you, and you can increase it, but it shouldn't be less than 1. And then yeah, after creating the box, and then we need 2 region for actually one of them for inlet and another for box, and this is specified the type of the neighbor, and we don't have any delay for creating generating the particle. And as you can see here, one of them, the first one, we have 2 type atom, and the first one is particle, and the second one is dye. And these are the material property of our particle. It should be defined like this: Young modulus, Poisson ratio, and here we define the actually the different type of the coefficient, friction coefficient for our particle, and the body of our or boundary and dye. As you can see, we define 0.3 for resistance coefficient, and for sliding friction coefficient we define 0.2, and for rolling coefficient I set 0. And as you can see here, core 11 means for actually for particle and particle, and actually if we have 2 type of particle, we can use here 1 for particle and particle, and 1 2 is for particle and dye, and vice versa, and 2 1 is dye and particle, and 2 2 for actually tools, means if we have punch and punch, but in here we don't have it. And also for all of them are the same. And also from this command we can define and specify our actually material property and coefficient, friction coefficient to our model, and Here we define the type of the an algorithm of contact. In this simulation we use per style Hertz tangential story actually for coefficient for contact method, and it is actually without cohesion, and we have a time step, and this is our time step. You should care about this actually about time step, and you have to consider it for generating the particle, and it can affect on the simulation result. And here we have another step for actually settle downing the particle, or somehow we can call it packing, or I use this number as a total, and the variation and other settle steps for this is the total time, and for steps we use this formula. After that we use gravity for model, and 120,000 for actually gravity, and you can change this number based on your case, and it is applied on z direction. And then here we recall or define our model, our geometry. As you can see, die, it should be like this one, it should define like this, and this is the name. Actually this is the path where you put your file, and this is the name of your steel. Type is 2 based on actually the type which is which was specified in here. And then we scale it with 0.1 because this is based on millimeter, and our input file is based on centimeter. And for actually inlet we use this name, and planar and file mesh, where we put the file and the name of the inlet, and the steel type 1, and also the scale for dimension. And here again for actually defining a determining the contact between inlet and the die, here we use this command for, and we have one actually part which is called die. We don't have any other other part like punch or something like that. We just only have dice, so we should put it here 1. If you have another part, you should put 2 or other. And now we should actually define our distribution. We have only one actually size of particle. PTS 1 means only we have one type of particle, and particle type is sphere. This number actually should be it is up to you and optional, but it should be actually not optional. We have to use this number, and this is not necessary only use this number. It should be more than 1. In some document they say that it should be more than 10,000. In some cases they should call they actually say that it should be more than 1 million. But I use this number, and you can find this number actually for in document. And the density constant I set 5,000, and the radius is actually I set the set is 80 micrometer. And here we define our distribution. PDD means for distribution, and particle distribution. Actually, again, this number is like this number, and you should define it. And we have only one type of particle. If you use more than one type of particle, you should increase this number based on your number of your particle used in the simulation. And then here we are defining the region for inlet. Actually, here we have our region dimension like this one. This is based on the actually the software that you were designing your inlet model, and we put the inlet at the height of 0.1 in our model. And this is for X, and this is for Y, and again this is for Z. And here we have to actually define the pouring system or generating model. These are somehow constant if you want to do the simulation like what I did, but if you want to do another kind of simulation, you should study the document and change these actually parameter. And this number again is like the above mentioned number, and the distribution the distribution template is the name of template we defined here. And max atom, you can increase it based on your work. Mass and mass rate, I use this number for mass and mass rate. And overlap check, you can actually use no or yes. In my case, I use yes for checking the overlap between the particle and constant velocity. In Z direction, I use this number. Actually, this number is based on your unit which you defined in the first of the input file. And then here you should define interface for as a the name for inlet, and extrude length means the height which you specify for actually the space which you specify for creating or generating the particle, which I will show you guys in the result. And here again you should actually again use for inlet the name for a sphere and inlet integer NVE group NV sphere. And here we use this command for defining the step or running part, run as one. And here we use for actually saving or storing the result as a VTK file, and every 100 increments somehow, if we can say like this. And here you shouldn't name actually specify the name of your job. And this is VTK as a extension. And here you should define your the output parameter that you needed, ID, type, XYZ coordinate, and again I don't know, velocity or F as a force, and mass and radius. And here we use this command for actually use a threshold or somehow termination time for our simulation. If our simulation reach to this number, actually the simulation was is stopped, and again this command is fixed and you should use it. And another step which we used is run settle step, as we defined here, for somehow settle downing the particle. Okay, this is the total IMP which I used for my model, and if you need further information, you can actually study the document in internet, but in my case actually I use this one. Let's start and let's run this simulation. And for running the simulation, you should actually define the path, and I use these command for actually providing any error, preventing any errors. And here for running the LIGGHTS software, and I copied these and paste it here and just enter. Okay, the simulation is being run and it's done. Okay, our simulation was done, and the number of particles is 304, and let's see the result. I use Paraview for seeing the result, and you should use these two. Apply. Okay. And radius, and set this one. Okay. Okay, as you can see, the particle start to pour when it reach at height of 0.1, and for, let me show you guys here. As I said, here from 0.1 up to around 0.3 or more than a little more is used for space for creating and generating the particle, which we defined in the actually input file. This is our actually this tutorial regarding the LIGGHTS simulation, DEM simulation for actually using LIGGHTS software. Please don't forget to subscribe our channel. As I already said, our channel needs your support and motivation. Please support us by your subscribe and like and introduce our channel to your colleague and friends, and I will actually create another tutorial regarding the how we can extract the data from Paraview and also for multi-distribution or multi-size particle in next time. Thank you so much for being with me until the end of this video, and see you. Bye bye.